Welcome to The Explainer. You know, every single day, massive companies are making billion-dollar bets on the future. How in the world do they do that? Well, today, we're going to pull back the curtain on the world of actuarial science, the profession that actually tames uncertainty and puts a price on risk. Okay, to kick things off, I absolutely love this quote from the physicist Richard Feynman. It just perfectly nails this huge shift in perspective. You know, these mind-bogglingly huge numbers, they're not just out there in space anymore. They're right here in our economies. And it's this vast universe of financial uncertainty that actuaries have to navigate every single day.
So, this really is the fundamental question, isn't it? It's the engine behind insurance, finance, pretty much everything we're about to talk about. How do you make a smart decision when you literally don't know what's going to happen next?
All right, so let's get into our first section. And we have to start with a core problem, our own intuition. When it comes to risk, our gut feeling is, well, a lot of the time, it's just plain wrong.
Okay, let's look at a classic thought experiment that really shows this in action, the St. Petersburg paradox. Picture this game. I'm going to flip a coin until it lands on heads. If I get heads on the first flip, you win $2. If it takes 2 flips, you get $4. 3 flips, $8. You get the idea. It doubles every single time. Now, if you do the math, the expected payout, the average you'd win over the long run, is infinite. So, what would you pay me to play? 1,000? A million? The funny thing is, most people wouldn't shell out more than, say, $20. That right there tells us we're not just simple calculating machines.
So, what in the world is going on there? Well, the answer comes down to something called expected utility theory. And the big idea is actually pretty simple. Money isn't all worth the same to us. Think about it. That first $1,000 you ever make? Life-changing. But adding another $1,000 when you already have 10 million? Barely noticeable. The satisfaction or utility you get from each extra dollar goes down. So even though the payout in that coin game could be infinite, the utility you get from it, not so much.
But, you know, even that theory isn't the whole story. Let's look at the Ayles paradox. Check out this first choice. You can have $1 million, guaranteed, or a tiny 1% chance of getting nothing, but with a shot at 5 million. Most people, they take the sure thing, option X. That 1% chance of zero is just too scary. Okay, now look at the second choice. It's a different setup, but here's the crazy part. Most people suddenly flip and pick W, the riskier option. Why? Because I guess the difference between a 10% and an 11% chance just doesn't feel that big. The paradox is that these choices are mathematically linked, but our brains just can't resist the siren song of 100% certainty. It has this powerful, almost irrational pull on us.
And this brings us to a really crucial point, which the incredible mathematician John von Neumann put perfectly. He said that sciences, and especially actuarial science, aren't really trying to explain the ultimate truth of the universe, they're making models. And the only justification for a model is, well, that it works. It's about being useful, not about being perfectly right.
All right, so for our next section, let's see how actuaries take these ideas about one person's weird decision-making and scale it up to manage an entire insurance portfolio with millions of policies.
And this is the massive challenge, right? An insurer isn't just dealing with one coin flip. They've got thousands, even millions of different policies. Car crashes, house fires, health issues. How in the world do you take all of those separate individual risks and mash them together to get one single picture of what the company might have to pay out in total?
So this table here, this shows you the old school way of doing it. The math behind it is called convolution. And it's basically this incredibly laborious process of layering one probability on top of another. I mean, just look at how complicated it gets combining only 3 simple policies. Now try to imagine doing that for 1 million of them. No way.
And this is where the modern world comes in. Today, actuaries don't do this by hand, thank goodness. They use these incredibly powerful computational tools like the fast Fourier transform and programming languages like R. They can run a function and do these massive calculations in, like the blink of an eye. What was once an impossible, theoretical nightmare is now just another Tuesday.
Okay, so all this computational power brings us into the modern actuaries world, where all this amazing theory gets to meet massive, massive amounts of real-world data.
I love this quote. It's hilarious, but it makes a really, really good point. The power we have in our computers today is absolutely mind-blowing. But it also means we're relying on these super complex models, and that introduces a whole new kind of risk. Because at the end of the day, the models are only as good as the data you feed them and the assumptions you make.
So how do they actually build these models? Well, they look for patterns in the data. Let's take car insurance, for example. Actuaries will sift through these enormous data sets to figure out what factors are actually linked to having an accident. They're looking at things you'd expect, like your age and where you live, but also the type of car you drive, maybe even your job, anything that can help build a more accurate statistical picture of your specific risk.
And the workhorse tool they use for this is something called a generalized linear model, or GLM. Now, I know this line of code on the screen looks a little scary, but it's really just a set of instructions for the computer. It's basically saying, hey computer, I want you to predict how often claims happen, and I want you to use these factors, sex, region, car type, to figure it out. The model then does the heavy lifting to find the exact mathematical relationship. It's all about finding that signal in all the noise.
Okay, for our final section, let's bring all this home. The paradoxes, the crazy math, the big data, it all serves one critical purpose: making absolutely sure that an insurance company can survive whatever the future throws at it and pay out every single claim it promised to.
And you know, one of the biggest, trickiest challenges here is something called IBNR. That stands for Incurred But Not Reported. Think about what that means. These are claims for things that have already happened. A car accident yesterday, a slip and fall last week, but the company has no idea yet. They literally have to put aside millions or even billions of dollars to pay for claims that are, for now, completely invisible.
So how do they predict the invisible? They organize all their past payment data into this structure you see here, called a runoff triangle. Each row is the year the claims came from, and the columns show how those claims developed and got paid out over the following years. The actuary's whole job is to be a detective, to use statistical models to spot the patterns and predict what numbers are going to fill in all those empty spaces.
And this isn't just some academic exercise. These predictions, filling in those blanks, they directly determine how many millions or billions of dollars a company is legally required to keep in the bank as reserves. If they get this number wrong, it's not just a bad day at the office. It could mean breaking the fundamental promise they made to their customers.
And get this, the margin for error they're working with is just razor thin. To get a top-tier AAA credit rating, an insurer has to prove that their models and their capital can withstand even the most extreme scenarios with 99.97% confidence. We're talking about having enough money to survive a once-in-a-3,000-year catastrophe. That's the level of certainty they're aiming for.
Which leaves us with one final, big question to chew on. We've gone from a simple coin flip all the way to these incredibly complex computer models. But as we get better and better at putting a number on the risks we already know, does that mean the world is actually getting less uncertain? Or are we just getting a clearer view of the next, even more complex uncertainties waiting just over the horizon?